Welcome back to the deep dive. Today we are cracking open a really hidden but vital world within industrial infrastructure.
That's right.
We're talking about something seemingly simple, but actually incredibly complex level measurement.
Yeah, just knowing how much stuff is in a tank.
Yeah,
Sounds easy.
exactly. How
Yeah.
much liquid, how much solid is in that tank or silo or vessel. But, the sources we've looked at really show that getting this wrong, well, it's not just inconvenient.
Well, it can be catastrophic or cost millions.
Yeah.
It really is the absolute foundation of reliable process control. Seriously.
If you don't get the level measurement right.
If you don't nail it, then everything downstream,
Yeah.
every automated action, every control decision, it's all based on bad data. It's flawed from the start.
So whether you're talking about, tracking inventory for sale custody transfer, they call it,
Right, where every fraction of a percent matters financially.
or making sure a chemical reaction gets the exact right amount of input.
Or just simply stopping a tank from overflowing and causing, an environmental mess or a safety hazard.
It all comes back to getting that level right. Precision starts here.
Absolutely. So our mission today, for you listening, is to sift through, I think we have 7 key technologies here.
7 major ones, yeah.
We want to understand the basic physics, the how it works behind each one, and critically give you the kind of criteria, the questions to ask to pick the absolute right tool for whatever demanding job you might face.
Okay, and we've got a real range here. We're talking high-tech radar, microwaves bouncing around, all the way down to like a simple vibrating tuning fork.
Quite the spectrum.
So to try and make sense of all this, we've kind of grouped things based on the science, right?
Yeah, that seemed logical. 3 main buckets. First, we'll look at the invisible wave systems. These are the non-contact ones using time of flight.
Okay, waves bouncing off the surface.
Right. Then second, we'll get more physical. Methods that actually touch the material or use a guide for, well, ultimate precision in tricky spots.
Contact methods, got it.
And finally, we'll loop back to some classics. The property-based measurements, things relying on pressure changes or electrical properties.
Sounds like a solid plan. Ready to dive into those invisible waves?
Let's do it. Where better to start than radar?
Yeah, when you think modern industrial measurement, especially for tuck jobs, non-contact radar often comes to mind first. It's kind of become the go-to, the benchmark.
It really has. Let's unpack the non-contact radar level transmitter.
Okay.
So, at its core, this is just applied physics, really elegant physics, actually. It uses the time of flight principle, TOF we call it.
Time of flight, like timing a bounce.
Exactly. But instead of, say, sound, we're using microwave radar pulses, electromagnetic energy.
Okay, microwaves. Like in the oven, but a different application.
Sort of. The transmitter, usually bolted onto the top nozzle of the tank or vessel, sends out a very short pulse of this microwave energy.
Down towards the material.
Precisely. It then listens, basically, waits for that pulse to hit the surface of the material, liquid or solid, and reflect back up.
And it measures the time that took.
Down to the nanosecond or even picoseconds. It measures that tiny, tiny time delay between sending the pulse and receiving the echo.
And that time directly relates to the distance.
Directly. Since we know the speed of light, that time delay translates perfectly into the distance from the transmitter to the material surface.
Bruh.
Subtract that from the known tank height, and boom, you have your level.
The beauty of using electromagnetic waves, those microwaves, becomes pretty obvious when you look where these things are used.
Oh, absolutely.
Our sources, they constantly highlight radar strength in environments that would just destroy other types of sensors.
Think about it. Highly corrosive acids. No problem. The sensor isn't touching it.
High pressure systems.
Yep, sits outside the pressure boundary.
Yeah.
Extreme temperatures, hot or cold.
Same logic. It's non-contact. It sits outside the tank, but it sees right inside.
Exactly. And what's really fascinating and maybe less intuitive is how resilient it is to what's going on inside the tank atmosphere.
You mean like vapors or dust?
Precisely. Radar signals, especially at the frequencies used, can largely penetrate or ignore things like light vapor layers rising off a liquid.
Right.
Or, say, the atmospheric dust you'd find inside a silo holding grain or plastic pellets. Even moderate amounts of surface foam often don't stop the signal completely.
So that inherent ability to cut through that noise makes it way more robust than, say, using sound waves.
Miles ahead in many cases. We'll get to ultrasonics later, but yes, radar's use of electromagnetic waves is a huge advantage in challenging process atmospheres.
Okay, but here's where it gets, as I teased earlier, really interesting. If it works so well through vapor and dust and even some foam, Why does it sometimes struggle? Like, why might it have trouble measuring certain chemicals, maybe highly refined fuels or some plastics?
Ah, you hit on the single most critical factor for selecting and applying radar, the dielectric constant of the material.
Dielectric constant. Okay, that sounds technical. Break that down for us.
It is technical, but the concept is key. Think of it as a measure of a material's ability to store electrical energy when it's in an electric field. But for radar, what it really governs is how strongly that material reflects the microwave signal.
So how well it bounces the signal back?
Exactly. Let's take water as the classic example. Water has a very high dielectric constant, somewhere around 80.
80. Okay, high number.
Very high. When a radar pulse hits a water surface, it's like hitting a mirror. The reflection is strong, sharp, and instantaneous. Easy to detect.
So measuring water or water-based liquids is generally pretty straightforward for radar.
Usually trivial, yes. But now, think about the opposite end. Materials like oils, many solvents, hydrocarbons, fine dry powders like flour, or even thick layers of foam.
They have low dielectric constants.
Very low. Sometimes down in the range of 1.5 to 3 compared to water's 80.
Big difference.
Huge. These materials tend to absorb or scatter the microwave energy instead of reflecting it cleanly. The result is a very weak echo, sometimes so weak that the transmitter struggles to distinguish it from background noise.
So if you're trying to measure, say, liquid propane or maybe fine plastic pellets.
You absolutely need to know that dielectric constant number first. If it's very low, say below 2 or 3, you might need a more sensitive radar, perhaps a higher frequency one, or you might have to concede that non-contact radar isn't the right choice for that specific material. Understanding that number is step one.
Okay, that makes sense. And you mentioned higher frequency radar. That brings us to this big shift we've seen in the industry from the older standard 24 gigahertz units to the newer 80 gigahertz systems. Why the jump? What does 80 gigahertz do better?
It fundamentally comes down to focus and resolution. Think of it like light.
Okay.
The traditional 24 gigahertz radars operate with a longer wavelength. This inherently creates a wider beam angle as the signal leaves the antenna, maybe 8 to 10 degrees wide.
Like a floodlight beam.
Good analogy.
Yeah.
It illuminates a relatively wide area on the surface. That's perfectly fine for large, simple, open tanks where you just need a general level.
But not all tanks are simple and open.
Far from it. Now, 80 gigahertz radar uses a much shorter wavelength. This allows the antenna design to create a dramatically narrower beam. We're talking maybe 3 or 4 degrees.
So going from that floodlight to more like a laser pointer?
Exactly like that. This tight focus gives you two major advantages in practice. First, better resolution. You get tighter accuracy, more stable readings, especially on low dielectric materials because you're concentrating the energy.
Okay, better accuracy. What's the second advantage?
The second is huge for real-world applications,
Hmm.
especially retrofits. That narrow beam allows you to precisely aim the radar to navigate around internal tank obstructions.
Ah, so things like ladders, pipes, agitator blades.
Exactly. Many industrial vessels, especially older ones, are just full of internal clutter heating coils, support beams, nozzles, dip tubes, you name it.
And the wide beam of a 24 gigahertz might hit those.
Easily. It might hit a support beam or the side of an agitator blade and generate a strong reflection. The radar system might then mistakenly think that reflection is the actual material surface.
Mhm.
That's a false echo, leading to a completely wrong level reading.
But the 80 gigahertz with its laser-like beam.
You can often mount it near the tank wall where there's clear space and aim that narrow beam precisely down into a clear spot on the liquid surface, completely avoiding the agitator shaft in the middle or the ladder on the side.
That seems like a massive practical benefit. You avoid needing to, I don't know, modify the tank internals just to get a good measurement.
It's a huge operational and cost saving. You upgrade your measurement accuracy and reliability without having to undertake expensive and disruptive vessel modifications. You're fitting the instrument to the tank, not rebuilding the tank for the instrument.
Okay, that makes the 80 gigahertz advantage very clear. But even with a narrow beam, tanks can be messy. Let's say you've aimed it perfectly, but there's still that big agitator blade sweeping underneath the beam path periodically. How does the transmitter ignore that? How does it know the difference between the moving liquid surface and this big metal thing moving nearby?
Right, good question. That's where sophisticated software processing comes in, specifically a feature usually called false echo suppression or sometimes tank mapping.
False echo suppression. How does that work?
When the radar unit is first installed and commissioned, typically the technician performs an empty tank mapping procedure.
Okay, mapping the tank when it's empty.
Exactly. The transmitter scans the empty tank, identifies all the strong, fixed reflections coming from known internal structures, the agitator at its resting position, nozzles, the tank bottom, support beams, weld seams, everything that doesn't move.
It learns the tank's internal geography, basically.
Precisely. It creates a digital map, a profile of these unwanted stationary echoes based on their distance, their time delay. It stores this map in its memory.
And then during normal operation,
During operation, when it receives echoes back, it constantly compares them against this stored map. If an echo comes back from a distance that matches a known mapped obstruction, it says, ah, that's just the agitator shaft, and it digitally filters it out, ignores it.
clever. So it only pays attention to the reflection that is changing, moving up and down, which must be the actual material surface.
That's the idea. It focuses on the dynamic echo from the true level, discarding the static noise from the tank internals. This ability to digitally tune out the clutter is absolutely essential for reliable measurement in complex real-world process vessels.
Okay, so non-contact radar, especially 80 gigahertz with false echo suppression, sounds like the high-performance option for tough jobs.
It often is. The Rolls-Royce, as you put it earlier.
But it's not the only non-contact player in the game. Let's pivot to its maybe more common, definitely more affordable sibling, the ultrasonic level transmitter.
Right. Ultrasonic. It shares the non-contact time-of-flight principle with radar. It sends out a pulse, waits for the echo, measures the time.
But the crucial difference is the type of wave it uses.
Absolutely crucial. Instead of electromagnetic microwave pulses, ultrasonic uses pulses of high-frequency sound waves, usually well above human hearing in the kilohertz range.
Sound waves, not microwaves.
Okay.
And the big advantage here is cost.
Primarily, yes. Ultrasonic transmitters are significantly less expensive than radar units. They can also be simpler electronically and sometimes easier to set up for basic applications.
So where do you typically see them used?
Their cost effectiveness makes them a really popular choice for less demanding applications. Think municipal water and wastewater treatment, measuring levels in open basins, sumps, weirs.
Okay, water levels?
Also very common for monitoring open channel flow, where level translates to flow rate. And they're frequently used for measuring the level of bulk solids, things like plastic pellets, grain, sand, and atmospheric silos, or bins where the conditions aren't too harsh.
Atmospheric being the key word there, maybe. Because the big downside, the Achilles heel of ultrasonic, seems to be its vulnerability to the environment inside the tank.
That is absolutely its key limitation.
If radar can handle some vapor and dust, why does ultrasonic struggle so much more with things like dust, steam, or even just temperature changes?
It boils down to the fundamental difference between electromagnetic waves and sound waves. Microwaves are energy propagating through an electromagnetic field. They don't strictly need a medium. Sound waves, however, are mechanical vibrations.
And they need something to travel through.
Exactly. They need a medium, typically air or the vapor space above the liquid, to propagate. And the speed of sound in that gaseous medium is incredibly sensitive to changes in the medium itself.
Okay, sensitive how? The sources mention lower accuracy than radar, but specifically point to temperature as a major issue.
Temperature is the killer app for ultrasonic inaccuracy, if you want to put it that way.
How bad can it be?
Well, consider this. The speed of sound in air changes by about 0.6 meters per second for every single degree Celsius change in temperature.
0.6 meters per second per degree C.
Okay. Now imagine you have a tall tank, maybe 10 meters, and let's say the ambient temperature up where the sensor is mounted is a nice 20 degrees C.
Okay.
But the processed liquid below is warmer, maybe heating the vapor space near the surface to 30 degrees C. That's only a 10-degree difference.
Seems plausible in many processes.
Very plausible. But that 10-degree gradient means the speed of sound isn't constant through the path the pulse travels. If the ultrasonic unit assumes a single speed based on the 20 degrees at the sensor head, its calculation of distance based on time will be wrong.
How wrong?
Over a 10-meter path, that 10-degree difference could easily introduce an error of, say, half a meter or more in the level reading. That's often completely unacceptable for process control.
Wow. So that feature you see listed on ultrasonic specs, temperature compensation, it's not just a nice-to-have bell or whistle.
It's absolutely mandatory, non-negotiable for any kind of accuracy.
How does it work?
They typically embed a small temperature sensor, like a thermistor, right near the ultrasonic transducer face. This sensor constantly measures the local temperature.
And feeds that back to the calculation?
Exactly. The transmitter software uses that real-time temperature reading to continuously adjust the value it uses for the speed of sound in its distance calculation. Time, distance, speed. It compensates for the temperature changes.
But even with compensation, it's still vulnerable to other things, right? Like steam or dust.
Highly vulnerable. Heavy steam or vapor can absorb or scatter the sound waves, preventing a clear echo from returning. Think of trying to shout through thick fog.
Right, the sound gets muffled.
Same idea. Similarly, thick dust clouds, like you might get when filling a silo with fine powder, can deflect the sound waves, again, preventing a reliable measurement. The sound pulse just can't push through effectively.
And what about pressure or
Right.
vacuum? Radar handles pressure, but ultrasonic.
Generally, no. Significant pressure changes alter the density of the gas medium, which changes the speed of sound in ways simple temperature compensation can't handle. And under a vacuum, there's no medium for the sound to travel through at all, so ultrasonic is pretty much limited to near-atmospheric pressure applications.
Okay, let's try to synthesize this first segment then. We've got two main non-contact time-of-flight players.
Yeah.
Non-contact radar uses electromagnetic waves. It's robust, great for harsh conditions, corrosive, high pressure, high temp. It cuts through vapor and dust pretty well. And the key differentiator within radar is frequency. 80 gigahertz gives you that narrow beam, essential for accuracy in tanks with internal obstructions. But you must know the material's dielectric constant.
Perfect summary. Low dielectric is radar's main challenge.
Then we have ultrasonic. It uses sound waves, much cheaper, simpler for basic tasks like water level or some solids in bins. And it's but it's highly sensitive to the environment. Temperature changes require mandatory compensation. Heavy vapor, thick dust, pressure variations, vacuum sheet. These are all major problems for ultrasonic.
Couldn't have said it better myself. Physics matters.
Indeed. So we've seen the power of sending waves through the air. But when does relying on that airborne signal become the problem itself? When you need to get physical?
Yeah, that's the perfect lead-in. Relying on that signal traveling through the vapor space becomes a liability in exactly the scenarios radar and ultrasonic struggle with.
Like the low dielectric materials we talked about for radar.
Precisely. When the dielectric constant is so low that even an 80 gigahertz radar can't get a strong enough reflection back through the air. Or, another case, when the liquid surface is extremely turbulent or covered in a very thick, dense layer of foam.
The waves just scatter everywhere.
Completely. The signal gets lost. In those situations, you need to move away from non-contact and look at our second category. Technologies that physically guide the measurement wave or rely on direct contact for precision.
Okay, and the first one here seems like a blend of the two worlds. Guided wave radar or GWR.
It really is a hybrid, yeah. It takes the fundamental time-of-flight microwave pulse principle from non-contact radar.
Okay, still using microwaves.
But instead of broadcasting that pulse through the air, it sends it down a physical probe, a metal rod, or a flexible cable that extends down into the tank and contacts the material.
So the probe acts like a waveguide, like guiding the signal directly to the surface and back.
Exactly. It's like putting the radar signal on rails. This waveguide, the probe, does two critical things. First, it eliminates the signal spreading you get with non-contact. All the microwave energy is contained along the probe.
Concentrating the energy.
Right. Second, because the energy is concentrated and guided, the reflection you get off the liquid surface, even a low dielectric one, is much, much stronger and cleaner than what non-contact radar could achieve through the air gap.
Ah, so if non-contact radar was struggling with, say, that refined oil or maybe some solvents because the reflection was too weak.
GWR can often handle them beautifully. The guided pulse has enough focused energy to get a clear, strong echo back, even from materials with dielectric constants down to maybe 1.4 or even lower in some cases.
So it overcomes the low dielectric problem. What about the turbulence and foam issue?
The probe helps there too. Because the wave is physically guided right down to the surface, surface turbulence or agitation has much less impact on scattering the signal compared to non-contact. Moderate foam is also less of an issue because the main reflection still occurs strongly at the liquid interface beneath the foam.
Okay, that makes sense. And the physical probe must make it ideal for really narrow spaces too, right?
Yeah.
Like small pipes or chambers.
Absolutely. Non-contact radar, even 80 gigahertz, needs some clear space. Try to shoot it down a narrow 2-inch standpipe or a bypass level gauge, and you'll get interfering reflections off the sidewalls immediately.
False echoes galore.
Exactly. But GWR, with its signal confined to the probe, works perfectly in those tight geometries. It's the go-to for bypass chambers and bridles on larger vessels.
Now, GWR has another trick up its sleeve that you mentioned non-contact radar can't really do reliably, measuring the interface between two liquids. How does one probe manage to see both the top level and the boundary below it?
This is a really powerful capability, especially in industries like oil and gas or chemical processing, where you have separators designed to split immiscible liquids, like oil and water.
Okay, how does it work?
So the guided microwave pulse travels down the probe. When it hits the surface of the upper liquid, let's say it's oil, which has a low dielectric constant, a portion of the signal reflects back. The GWR detects this first echo and calculates the top level.
Okay, first reflection is the top level.
But because the oil's dielectric is low and the guided pulse is strong, a significant amount of the energy continues through the oil layer. It keeps traveling down the probe
Until it hits the next layer.
until it hits the interface, the boundary, with the second liquid below, typically water in these applications, which has that very high dielectric constant.
Ah, a big change in dielectric.
Exactly. That sharp change in dielectric constant at the oil-water interface causes a second, very distinct reflection. The pulse bounces strongly off the water layer.
And the GWR sees both echoes.
Yes. The electronics are sophisticated enough to detect and time both reflections, the weaker one from the top oil surface and the stronger one from the oil-water interface. By measuring the time delays to each, it can calculate both the overall top level and the level of the interface layers simultaneously using just one instrument.
That is genuinely impressive. A huge capability for process control and separators.
It really is.
But there's always a but. The compromise here is obvious. You now have a physical probe, a piece of metal, sticking down into your process fluid.
That is the fundamental trade-off. You gain the advantages of guided energy, low dielectric measurement, and interface detection, but you lose the non-contact benefit.
Which immediately rules out certain applications.
Definitely. Sticky, viscous materials that could heavily coat the probe are a problem. Things like asphalt, thick polymers, molasses, they can gum up the probe and attenuate the signal or even prevent measurement altogether.
And solids, bulk solids.
Generally not suitable for GWR. Abrasive solids could damage the probe, and powders could build up unevenly or exert sideways forces, potentially bending or breaking the probe, especially longer cable types. GWR is primarily for liquids and possibly some very light slurries.
Okay, and you don't just stick any old probe in there, right? The sources mention different probe types.
Correct. Selecting the right probe type is critical and depends heavily on the application and, again, the dielectric constant of the material.
What are the main types we see?
Generally, there are three common ones: a single rigid rod, a twin rigid rod, or sometimes parallel cables, and a coaxial probe.
Okay, single rod, twin rod, coaxial. What's the difference?
The single rod is the simplest, most robust mechanically. It's great for general-purpose liquid level, especially when the liquid has a medium to high dielectric constant. It relies on the tank wall acting as the second conductor, essentially.
Makes sense. Twin rod.
Twin rods or cables create a more defined electromagnetic field between them. They can offer slightly better performance in certain conditions, maybe very large tanks or where grounding is difficult. But the real specialist is the coaxial probe.
Coaxial. Like a coax cable for TV.
Exactly the same principle. It's essentially a central rod conductor surrounded by an outer metallic tube with insulating spacers. The microwave pulse travels entirely within the space between the inner rod and the outer tube.
So the signal is completely contained.
It's completely contained. This design maximizes the signal strength and completely shields it from any external interference or reliance on the tank wall.
When would you absolutely need a coaxial probe?
You typically need a coaxial probe when you're measuring materials with extremely low dielectric constants. We're talking below 1.7, sometimes even down to 1.4. Things like liquefied gases, LNG, LPG, very pure solvents, or some light hydrocarbons. The coax ensures enough signal gets back for a reliable measurement.
Got it. Single rod for general use, coax for the really tough, low dielectric stuff. Now, even with the right probe, over time, you're going to get some coating or buildup in many processes, right?
It's almost inevitable in many applications, especially with things like crude oil, some chemicals, or even hard water scale.
You mentioned earlier that non-contact radar has false echo suppression. Does GWR have something similar to deal with this coating problem? You mentioned compensation algorithms.
Yes, it's a different challenge than false echoes, but there is compensation. Coating, especially if it's conductive or significantly changes the dielectric properties right around the probe, can cause signal loss, attenuation, and inaccurate readings.
So how does the GWR fight back?
Advanced GWR transmitters have very sophisticated signal processing built in. They don't just look for the peak of the reflection, they analyze the entire reflected waveform shape, its strength, and how it changes over time. If a coating builds up relatively uniformly and stably, the system can learn the effect that coating has on the signal attenuation. It essentially characterizes the signal loss caused by the coating.
And then adjusts the reading accordingly.
Exactly. It applies algorithms that mathematically compensate for that known attenuation, effectively seeing through the buildup to calculate the true liquid level underneath.
That sounds incredibly useful for maintenance.
It's huge. It means you don't necessarily have to pull the probe out for cleaning every time a thin layer builds up. It extends the maintenance intervals significantly, reducing downtime and labor costs. It makes GWR viable in processes where it might otherwise be considered too high maintenance.
Okay, so GWR sacrifices non-contact for better precision on low dielectrics, handles turbulence foam better, does interface, but needs the right probe and careful consideration of coating.
A very good summary.
Now let's move to another contact technology, one that achieves perhaps even higher accuracy, not with microwaves, but with magnets and a fascinating physical effect. Magnetostrictive level transmitters.
Ah, yes, magnetostrictive. This is a really neat piece of engineering, and as you say, it's known for exceptionally high accuracy and repeatability.
So how does it work? Magnets and what was the word? Magnetostriction.
Magnetostriction, yeah.
Yeah.
It's a property of certain ferromagnetic materials where they change shape slightly when exposed to a magnetic field. Here's the setup. You have a sealed outer tube, often stainless steel, installed vertically in the tank. Inside this tube, riding on the liquid surface, is a float.
Okay, a float that moves up and down with the level.
Exactly. And crucially, sealed inside this float is a set of strong, permanent magnets.
Magnets in the float. Got it.
Also inside the outer tube, running down its center, is a special wire made of a magnetostricted material. This is called a waveguide wire.
Waveguide wire. Okay.
Now, the electronics unit at the top of the transmitter does something clever. It sends a very brief electrical current pulse down this waveguide wire.
A quick zap of electricity down the wire.
It's the short burst. Now, physics time. When that current pulse travels down the wire, it creates a temporary circular magnetic field around the wire.
Okay, current creates a magnetic field. Standard physics.
Right. And remember the float. It has strong permanent magnets creating a vertical magnetic field at the location of the float.
So you have the wire's circular field meeting the float's vertical field.
Exactly. Where those two magnetic fields intersect right at the position of the float, something remarkable happens due to the magnetostrictive property of the wire. It generates a tiny, localized mechanical twist, or torsional strain pulse, in the wire itself.
A physical twist in the wire generated by the magnetic fields interacting.
Precisely. It's called the Wiedemann effect, a specific type of magnetostriction. This tiny twist, this strain pulse, then travels along the wire as a mechanical wave, both up towards the sensor head and down towards the bottom.
And the sensor is listening for that twist to arrive back.
It's listening for the upward traveling twist. It measures, again with incredible precision, think picoseconds the time it takes from sending the initial current pulse to receiving that returning torsional strain pulse at the sensing element in the head.
And like radar, time equals distance.
Exactly. The speed of this mechanical torsional wave in the specific waveguide wire is very stable and precisely known. So the time delay directly corresponds to the distance from the sensing head down to the float's position, giving you the liquid level.
Okay, unpacking the aha moment here. The core advantage seems to be this incredible precision based on timing that mechanical twist.
That's absolutely it. Because you're timing a physical waves in a solid controlled medium, the wire, the measurement is inherently very stable and highly accurate. We're talking accuracies often quoted in the range of 0.01% of the measuring range, or even better, fractions of a millimeter sometimes.
That's why it's used for those really critical applications.
Absolutely. Custody transfer, where you're buying or selling large volumes of valuable product like oil or chemicals, and tiny errors add up to big money. High accuracy inventory management, especially in industries like pharmaceuticals, where precise batching is critical. Anywhere that needs undeniable accuracy and repeatability.
What's really striking is comparing it to, say, DP or even radar. Magnetostrictive seems immune to changes in the fluid's properties, doesn't it?
That's another major advantage. Think about it. The measurement relies on the float's position and timing the twist in the wire. It doesn't care about the liquid's density, its dielectric constant, its viscosity, as long as the float moves freely, or the pressure and temperature of the process fluid or vapor space.
So temperature swings, pressure changes, different product batches, none of that affects the reading.
As long as the float is floating at the right level, the measurement remains accurate. The physics is happening in the wire, independent of the surrounding fluid's changing properties. That's a huge plus for reliability in dynamic processes.
We talked about interface measurement with GWR. Can magnetostrictive do that too? Is it better?
It can, and many would argue it's superior, especially for sheer resolution and accuracy of the interface position.
How does it do interface? Two floats.
Exactly. You use a specially designed dual float system. You have the standard top float that rides on the upper liquid, say oil. Then below it, you have a second heavier float. This bottom float is carefully weighted so that it sinks through the top liquid but floats on the denser bottom liquid, say water.
So one float tracks the top level, the other tracks the interface.
Correct. Each float has its own set of magnets. The transmitter sends its current pulse, and it gets two distinct torsional strain pulses back, one from the top float's magnets and one from the bottom float's magnets.
And just times both.
It times both precisely, giving you highly accurate, simultaneous readings of both the total level and the interface level. Because of the inherent timing precision, dual float magnetostrictive is often considered the gold standard for critical interface applications, demanding the utmost accuracy.
Okay, supreme accuracy, interface capability, immunity to fluid property changes. What are the limitations? Must be similar to GWR in terms of needing contact.
Very similar constraints, yes. First, installation is critical. The transmitter tube must be mounted perfectly vertically. Any significant leaning can cause the float to bind or stick inside the tube.
So no angled installations?
None. Second, like GWR, it requires contact, and the float needs to move freely. This makes it unsuitable for liquids that are very sticky, highly viscous, or that tend to crystallize or leave heavy deposits. Anything that could gum up the float's movement is a showstopper.
And solids are definitely out.
Absolutely out. Solids would pack around the float chamber, preventing movement entirely. Magnetostrictive is fundamentally a clean liquid measurement technology. You need a relatively clean liquid where a float can move reliably up and down.
All right, we've navigated the invisible waves of radar and ultrasonic, and we've gotten hands-on with the guided precision of GWR and magnetostrictive. Now we move to our third and final category.
Yep, shifting gears a bit.
These technologies don't look at wave travel time. Instead, they measure a fundamental property of the material itself, or the column of material. We're talking pressure and electrical capacitance.
Exactly. And we have to start with the oldest, most widely installed, and often incredibly resilient workhorse in the process plant.
Right.
The differential pressure, or DP, level transmitter.
DP level, it feels like it's been around forever.
Pretty much since the dawn of process automation. It's based on fundamental hydrostatic physics. Simple, but effective.
So how does measuring pressure tell you the level?
It relies directly on that high school physics formula. Pressure equals density times gravity times height. P comes right.
Okay, pressure depends on the height of the liquid column and its density.
Precisely. A DP level transmitter doesn't just measure pressure at one point, it measures the pressure difference. That's the differential part between 2 points in the tank. Typically, it measures the pressure near the bottom of the liquid column. This is the high pressure, or HP, connection, and compares it to the pressure in the vapor space at the top of the tank, the low pressure, or LP, connection.
So it's measuring the pressure exerted only by the liquid column itself.
Exactly. By subtracting the top pressure, LP, from the bottom pressure, HP, it isolates the pressure caused purely by the height, or head, of the liquid. This pressure difference, HP delta P, is directly proportional to the liquid level, H. The formula boils down to level H, wheels still PHE.
Level equals the pressure difference divided by density and gravity. Seems straightforward.
The principle is straightforward, and because you're fundamentally just measuring pressure, DP sensors can be incredibly robust.
That's their big advantage, right? Proven, reliable technology.
Decades of proven reliability. They can handle very high pressures and extreme temperatures, especially when used with protective remote seals, which we'll get to. They work fine in pressurized tanks. They're often the default choice for large vessels where other technologies might be too expensive or struggle.
That formula you mentioned, HBPHG, there's a variable in there that screams potential problem.
Ah, you spotted it. Density.
Tell us about that calibration challenge. This seems like the absolute key weakness of DP level.
It is the Achilles heel. The entire accuracy of the DP level measurement hinges on the liquid density remaining constant and critically known. The transmitter is configured with a specific density value for the liquid it's measuring.
But what if the density changes?
Then your level reading is immediately wrong. Think about temperature. Most liquids expand when heated and contract when cooled.
Meaning their density changes?
Exactly. If the process temperature fluctuates significantly, the liquid density changes. But if the DP transmitter is still using the old fixed density value in its calculation, the calculated level, H equals Karug, will drift, even if the actual level hasn't changed at all.
So for processes with big temperature swings, or maybe where they're blending different products?
DP level becomes problematic. You might need external temperature sensors feeding into the control system to dynamically compensate the density value, which adds complexity. Or, if the density changes are unpredictable or too large, engineers often abandon DP for level and switch to a technology that's independent of density, like radar or magnetostrictive.
And DP is pretty much useless for solids, right? You can't rely on hydrostatic pressure from a pile of powder.
Correct. DP is strictly for liquids where you can assume a consistent hydrostatic head pressure relationship.
Okay, density dependence is the big weakness. Now, installation also seems way more involved than just bolting a radar onto a top flange. You need two pressure connections, HP and LP.
Yes, proper installation is crucial for DP accuracy. And the setup differs depending on whether the tank is open to the atmosphere or if it's a closed, pressurized vessel. This leads to the concepts of dry leg versus wet leg installations.
Dry leg versus wet leg. Let's start with the simpler one, presumably dry leg.
Right, you use a dry leg setup on an open, non-pressurized tank. Here, the vapor space above the liquid is just open to the atmosphere.
So the pressure at the top is essentially zero gauge pressure.
Correct. In this case, the low pressure LP port of the DP transmitter can simply be left open to the atmosphere or connected via an open impulse tube that runs up to the top of the tank, just to ensure it's referencing the same atmospheric pressure. The leg is dry because it just contains air.
Simple enough. But most industrial process tanks are closed, often under pressure or vacuum. You can't just leave the LP side open then.
Absolutely not. If you did that on a pressurized tank, the LP side would just read atmospheric pressure, while the HP side reads the liquid head plus the tank's vapor pressure. Your AP reading would be completely wrong and would fluctuate wildly with any change in tank pressure.
So for closed or pressurized tanks, you need the wet leg setup.
Yes, the wet leg is essential here. What you do is run an impulse line from the top vapor space connection down to the L key port of the transmitter, just like you run a line from the bottom tap to the HP port. But critically, you must completely fill this LP impulse line with a stable, non-volatile reference fluid.
Fill the low pressure line with a specific liquid. Why?
You fill it with a reference fluid that has a stable, known density and won't freeze or boil at process conditions, often something like glycol, water, if freezing isn't an issue, or a specific fill fluid. This creates a constant, known hydrostatic pressure head on the LP side of the transmitter.
So the LP side isn't reading zero or fluctuating gas pressure anymore. It's reading the constant pressure from this reference fluid column.
Exactly. Now, the DP transmitter is measuring the difference between the HP side, process liquid head plus vapor pressure, and the LP side, wet leg reference fluid head plus vapor pressure. The vapor pressures cancel out.
Clever. So the LP reading now only reflects the difference between the process liquid head and the fixed reference leg head.
Precisely. It effectively isolates the measurement from the tank's operating pressure, allowing you to accurately calculate the level based purely on the changing process liquid head relative to that fixed wet leg reference. It stabilizes the whole measurement.
That's much more complex than dry leg, but clearly necessary. But wait, what if the process fluid itself is nasty? Corrosive, super hot, or so thick it would clog those impulse lines?
Good point. You absolutely do not want to run something like concentrated sulfuric acid, molten sulfur, or heavy polymer directly into the sensitive diaphragm and tiny passages inside a DP transmitter.
You destroy it or plug it instantly?
Right. That's where remote seals come in. They are a crucial safety and maintenance accessory.
How do remote seals work? They isolate the transmitter.
They do. A remote seal system consists of a diaphragm, usually made of corrosion-resistant metal, that bolts directly onto the tank nozzle, one for the HP tap, one for the LP tap. This diaphragm is connected to the DP transmitter via a sealed capillary tube.
A thin tube, filled with what?
Filled with a specific, incompressible, thermally stable fill fluid like silicone oil or glycerin. The process pressure pushes on the external side of the diaphragm seal. This pressure is hydraulically transmitted through the fill fluid in the capillary tube directly to the measuring diaphragm inside the DP transmitter body.
So the transmitter feels the pressure, but the nasty process fluid never actually touches it.
Exactly. The remote seal diaphragm and the fill fluid act as a barrier, safely isolating the transmitter while accurately transmitting the process pressure. It's essential for corrosive, viscous, high-temperature, or plugging surfaces.
Okay, DP requires careful thought about wet versus dry legs and potentially remote seals. Now, one last piece of DP setup jargon: zero suppression and zero elevation. This sounds like calibration tweaking.
It's fundamental calibration, yes, and it's all about compensating for where the transmitter is physically mounted relative to the tank taps, especially the 0 point, usually the bottom tap or the desired 0% level. Think about stepping on a bathroom scale. You want to read 0 before you put any weight on it.
All right, you zero the scale.
Same idea here. Let's say your bottom tank connection, your 0% level point, is at a certain height. But for installation convenience, you have to mount the DP transmitter above that bottom tap, maybe 1 meter higher up the wall.
Okay, transmitter is higher than the 0 point.
When the tank is actually empty, 0% level, the HP impulse line running down from that tap to the transmitter is full of liquid. This liquid column exerts a positive pressure head on the HP side, even though the tank is empty. The transmitter would incorrectly read a positive level.
It thinks there's liquid when there isn't because of the pipe drop.
Exactly. To fix this, you apply zero elevation. This is a negative offset programmed into the transmitter. You tell it, subtract the pressure equivalent of that 1 meter of fluid head so that when the tank is truly empty, you read 0.
Okay, zero elevation subtracts pressure when the transmitter is mounted below the 0 tap. What about zero suppression?
That's the opposite case. Imagine you mount the transmitter below the bottom tap. Now, when the tank is empty, the HP port is actually lower than the liquid surface would be at 0%. It sees less pressure than it should at 0. Or think about the wet leg scenario. That reference fluid in the LP leg is exerting pressure even when the tank is empty.
So you need to add an offset.
Correct. You apply zero suppression, which is a positive offset. You tell the transmitter, add this amount of pressure to your reading to account for the fact that the reference point is effectively lower, or to cancel out the constant pressure from the wet leg so that you read 0 when the process level is actually at 0%. Getting the elevation or suppression right is critical for the DP reading to be accurate across its entire range. Wow. DP level. Simple principle, but the practical execution involves a lot of careful physics and setup. Density, wet legs, dry legs, seals, elevation, suppression.
It's a testament to how fundamental pressure measurement is, but yeah, it requires understanding the details.
Okay, let's move from pressure to electricity. Our next property-based sensor is the capacitive level sensor.
Capacitive sensing. This is another elegant, often simpler approach, especially compared to DP installation. No moving parts.
How does capacitance tell you the level? It works based on the electrical principle of a capacitor. A basic capacitor is just two conductive plates separated by an insulating material called the dielectric. The amount of electrical charge it can store, its capacitance, depends on the size of the plates, the distance between them, and the properties of that dielectric material.
Okay, so how does that apply to a tank?
In a capacitive level system, the sensor probe itself, usually a metal rod or cable inserted into the tank, acts as one plate of the capacitor. The metal tank wall usually acts as the second plate, or sometimes a reference tube is used.
And the material in the tank is the dielectric.
Exactly. The liquid or solid material between the probe and the tank wall is the dielectric medium. Now here's the key. The material being measured, say oil, has a different dielectric constant than the air or vapor in the empty space above it.
Ah, so as the level of material goes up.
As the level rises, more of the space between the probe, plate 1, and the tank wall, plate 2, gets filled with the material, the dielectric, and less is filled with air vapor. Since the material has a different dielectric constant than air, the overall capacitance of this probe wall system changes.
And that change in capacitance is proportional to the level.
Directly proportional. The electronics measure this change in capacitance and convert it into a level reading, typically a standard 420 mA analog signal.
Seems quite neat. Where is it typically used? What kind of materials?
Capacitive sensors are great for liquids that have low electrical conductivity, things like oils, solvents, and chemicals. They're also very widely used for measuring the level of bulk solids and powders. Think flour, cement, plastic pellets, grains.
Solids again, unlike DP or magnetostrictive.
Right. They offer a relatively simple, compact, and often lower-cost way to get continuous level measurement in silos and bins, especially compared to radar for solids. No moving parts means good reliability in principle.
But, like GWR, which also uses a probe, capacitance must have issues with coding, right? But maybe for electrical reasons this time?
Yes, sensitivity to coding is arguably the biggest disadvantage of capacitive sensors. And you're right, it's often related to conductivity.
How so?
If the material coats the probe, especially if that coating is conductive, like many water-based slurries or sticky materials, that buildup can essentially short-circuit the capacitor. The coating acts like an unwanted conductive path between the probe and the wall, drastically changing the measured capacitance and causing severe signal drift or complete failure.
So sticky conductive stuff is bad news for capacitance.
And very bad news. Proper grounding of the tank and probe is also absolutely critical for capacitance to work reliably. Furthermore, just like radar depends on the dielectric constant, capacitance does too, but perhaps even more sensitively.
How is it more sensitive?
Remember, the measurement is the changing capacitance due to the dielectric. If the dielectric constant of the material itself changes slightly, maybe the moisture content in your grain changes from one batch to the next, or the composition of your liquid varies. The capacitance will change, and your level reading will be inaccurate unless you recalibrate.
So consistency of the material's electrical properties is key.
Very key. Selection really boils down to knowing the material's dielectric constant and how stable it is, and assessing the risk of conductive coating.
Is there anything they do to fight that coating problem, like a compensation in GWR? You mentioned a guard electrode in the notes.
Yes, the guard electrode. This is a more advanced feature you find on some capacitive probes, often used in sanitary food applications where buildup is common but needs to be managed.
How does a guard electrode work?
Essentially, a section of the probe near the process connection, or sometimes near the tip, is electrically isolated from the main measuring section. This guard section is actively driven by the electronics to be at the same electrical potential voltage as the main sensing element.
Okay, guard is at the same voltage as the sensor, so what does that do?
Because there's no voltage difference between the guard and the sensor, any electrical current flowing through the coating buildup in that guard area is effectively shunted or diverted away from the main measurement circuit. It forces the capacitance measurement to focus only on the dielectric change further down the probe, ignoring the effects of the coating near the top.
It doesn't stop the coating, but it stops the coating from messing up the reading.
Exactly. It significantly reduces the error caused by uniform coating, making the measurement much more stable and reliable, even with some buildup. It's a clever way to improve performance in tricky coating applications.
Okay, capacitive. Good for low conductivity liquids and solids. Simple, no moving parts, but highly sensitive to coating, especially conductive, and changes in dielectric constant. Guard electrodes help with coating.
Well put.
That brings us to our final technology. And you stressed earlier, we need to make a really crucial distinction with this one. The tuning fork, or vibrating fork, level switch.
Yes, absolutely critical distinction for anyone listening. Everything we've discussed so far, radar, ultrasonic, GWR, megadistrictive, DP, capacitive, these are all technologies designed for continuous level measurement.
Meaning they give you an analog output like 420 milliamps that tells you the level is at 10%, 50%, 93%, whatever it is.
Precisely. They track the level as it moves up and down. The tuning fork does not do that. It is not a continuous measurement device.
Okay, so what is its purpose then?
Its sole purpose is point level detection. Think of it as a simple, incredibly reliable switch. It only tells you one thing. Has the material reached this specific point, yes or no?
Okay, let's unpack this. So it's purely binary. It doesn't care if the level is 1% below the fork or 50% below. It only cares if the material touches it.
Exactly that. It's an alarm system, not a gauge. Inside the device, there's a metal fork shaped like a tuning fork that is made to vibrate constantly at its specific resonant frequency, usually driven by a piezoelectric crystal.
Vibrating at a fixed frequency.
Okay. This vibration is typically at a high frequency, maybe a few hundred hertz or even into the kilohertz range, well above audible levels. The electronics continuously monitor this vibration frequency.
And when the material hits the fork?
When the processed material, whether it's a liquid or a solid powder or granule, comes into contact with the vibrating fork tines, it physically dampens the vibration, it absorbs the energy.
Like putting your finger on a ringing bell.
Perfect analogy. That damping causes a distinct, measurable change in the fork's vibration. Either the frequency shifts slightly or the amplitude decreases significantly. The electronics detect this change instantly.
And that triggers the switch.
That triggers an internal relay or electronic switch, changing the output state. It sends a simple digital signal on or off, contact open or close to the control system, or an alarm panel.
So its applications are purely for things like alarms.
Exactly. High-level alarms to prevent tank overflows, low-level alarms to protect pumps from running dry, point-level detection to confirm presence or absence of material in chutes or pipes, basic switching functions. Anywhere, you need a simple, reliable yes-no indication at a specific level.
Given its simplicity, why choose a tuning fork over, say, a small, cheap capacitive switch or even a mini radar for a critical high-level alarm? What makes it so reliable?
Its robustness and immunity to process conditions are unmatched for point-level switching. Think about all the things that troubled the other technology.
Dielectric constant.
It doesn't matter to a tuning fork. As long as the material is dense enough to dampen the vibration, it works. Doesn't care if it's water or oil or plastic pellets.
Foam, vapor,
Ah,
turbulence.
generally immune. Light foam might be ignored, heavy foam will dampen it. Vapor is irrelevant. Turbulence doesn't affect the physical vibration significantly.
Coating, electrical properties.
Minor coating is usually ignored as long as the tines can still vibrate freely until the bulk material arrives. It's not relying on electrical conductivity or capacitance. It's purely mechanical damping.
And calibration.
It requires virtually no calibration. You install it at the height you want the alarm, wire it up, and it works. That inherent simplicity and immunity make it incredibly reliable, especially for safety-critical applications like safety instrumented systems, SIS.
That reliability sounds key. And there's a specific safety feature related to power loss too, right? Fail-safe mode?
Yes, and this is crucial for safety switches. Fail-safe mode ensures the switch provides a safe, predictable output state in case of an internal malfunction or, more commonly, a loss of power to the instrument.
How does that work?
It's designed so that the normal operating state, when the fork is vibrating freely, maybe indicating no alarm, requires power to maintain the output relay in one position. If the power fails, or if the internal electronics detect a fault, like the crystal failing, the relay automatically drops into the opposite state, the alarm state.
So if it's a high-level alarm switch, losing power makes it signal high level.
Exactly. It defaults to the safest condition. The control system sees the alarm signal and knows either the level is actually high or the switch itself has failed or lost power. Either way, it triggers the appropriate safe response, like closing an inlet valve, preventing a potential overflow, even if the instrument itself is offline.
That's a critical design feature for safety interlocks.
Absolutely. You always want safety devices to fail in a way that alerts the system to a potential problem.
Okay, that perfectly contrasts our last two then. The tuning fork is the ultra-reliable install-and-forget point-level switch. Perfect for critical alarms, immune to most process variables, requires no calibration, fails safe, but only gives you that one alarm point.
The dependable watchdog.
While the capacitive sensor offers continuous measurement, is good for powders and low-conductivity liquids, relatively simple, but it's very sensitive to coating, grounding, and any changes in the material's electrical properties.
Two very different tools for different jobs, both relying on fundamental properties. So we've journeyed through quite a range of technologies, haven't we? From microwaves bouncing off surfaces miles away technically, down to a tiny fork vibrating in the fluid.
A huge range: radar, ultrasonic, GWR, magnetostrictive, DP, capacitive, tuning forks.
Yeah. And I think the most crucial takeaway, the message we really want you, the listener, to internalize from this deep dive, is that there's absolutely no single best technology. There just isn't.
It always depends.
It always depends. The right answer, the optimal choice, is always going to be a result of carefully analyzing your specific situation. It's a function of the process conditions, temperature, pressure, the tank or vessel geometry size, shape, internal obstructions, and critically, the specific chemical and physical properties of the material you're trying to measure.
Density, dielectric constant, viscosity, conductivity, tendency to coat. Is it a liquid? Is it a solid?
All of those factors weigh into the decision. You have to match the physics of the sensor to the physics and chemistry of the application.
Okay, let's try to crystallize that with a quick final summary, sort of a cheat sheet based on common scenarios.
Good idea. Let's run through some common challenges.
All right, scenario one. You've got a really nasty corrosive fluid. It's in a tank that's under high pressure, maybe high temperature too. What are your top contenders?
Your choices narrow down quickly there. Need non-contact or something robustly isolated. Top of the list is non-contact radar, especially 80 gigahertz if there are internals. Or the classic differential pressure DP transmitter, and this is critical installed properly with chemically compatible remote seals to protect the transmitter itself.
Okay, radar or DP with seals for the really tough stuff. Scenario two, your absolute priority is precision. Maybe it's custody transfer billing or super accurate batching. Or you specifically need to measure an interface level very accurately.
For top-tier accuracy and repeatability, especially for valuable inventory or interface, magnetostrictive is hard to beat. If you need interface measurement, but the environment is maybe a bit more turbulent or foamy, guided wave radar, GWR, is your strong second option, provided the liquid isn't too sticky or likely to heavily coat the probe.
Got it. Magnetostrictive for ultimate precision, GWR as the rugged interface alternative. Scenario 3. You're measuring bulk solids, powders, grains, plastic pellets, probably in a silo or bin at normal atmospheric conditions. Cost is likely a factor.
Here, you're leaning towards the more cost-effective options. Ultrasonic is a common choice if you're confident about managing dust levels and temperature compensation is adequate. Capacitive sensors are also very strong contenders for solids and powders. Again, if you've assessed the risk of coating and know the dielectric constant is stable enough for your accuracy needs.
So ultrasonic or capacitive for bulk solids, but with those environmental and material property caveats.
Exactly. Always check those caveats.
Final scenario. Your goal isn't continuous measurement at all. You just need a rock-solid, guaranteed warning signal. A high-level alarm to prevent a spill or a low-level alarm to save a pump. Reliability is everything.
No question there. For a simple, ultra-reliable digital point-level alarm, you choose the tuning fork switch. Its immunity to process variables and lack of calibration make it the go-to for safety-critical on-off detection. Install it, wire it, trust it.
Perfect. That really helps tie the selection criteria to the technology.
Hopefully clarifies the decision tree a bit.
So our deep dive today, we've gone to a lot of detail on how to measure the level and sometimes that interface boundary between liquids. But let's leave our listeners with maybe one final thought to chew on.
Okay.
Consider the enormous importance, the sometimes astronomical stakes, riding on the data coming from these seemingly simple sensors. Think about chemical separation processes where efficiency depends on holding that interface level just right.
Or custody transfer, where millions of dollars change hands based on that level reading, translating to volume. 0.1% error isn't trivial anymore.
Exactly. A slight, unanticipated change in density throwing off a DP reading, or maybe some unexpected moisture changing the dielectric constant for a capacitive or radar sensor. These aren't just small instrument errors. They can ripple outwards into massive financial losses, off-spec product, or even, in the worst cases, safety or environmental incidents.
The consequences can be huge.
So the real takeaway, perhaps, is that you, the listener who's followed along, you now understand something crucial. Mastering modern process control, especially level measurement, isn't just about knowing the latest sensor technology or bolting on the fanciest transmitter.
It's deeper than that.
It's about truly understanding the underlying physics and chemistry, knowing why a radar reflects, how pressure relates to density, what makes a fork stop vibrating. It's about ensuring the fundamental principle of the sensor you choose is genuinely suited to the unchanging physics of the material and the process you're putting it into. That's where true mastery lies.
Well said. The sophistication isn't just in the sensor hardware. It's in the application knowledge, the math, the physics behind it all.
Indeed. And that's our deep dive for today. We'll see you next time.